mirrors by analyzing the simplest one, which is conveniently called the simple current mirror. By the way, that name is a warning. There might be a few complicated current mirrors out there, so let's enjoy our time with this one. The simple current mirror is pictured on the left here. The title gives away its big trick, which is that the current I out is forced to be the same as the I in current source. The heart of that trick is that VB is a one-to-one function of IC. So the I in current source creates some amount of IC1 in Q1, which is diode connected. And that means that VB has to be set to whatever value produces IC1 in transistor Q1. And that's captured by this pair of equations. This is our usual IC1 expression for BJTs, and if you invert it, you find that the base to emitter voltage is a one-to-one function of the collector current, and specifically a logarithmic function of it. That means the IC1 current must match the IC2 current, because both transistors share the same base voltage VB, which we already know is appropriate to create IC1. So great! Now all we need to do is find the relation between IC1 and I in. Though before we do that, I want to take a tiny aside to mention that current mirrors are an interesting structure, because you can argue they use a technique called pre-distortion. Q1 converts I in to VB through a nonlinear function, and Q2 uses the inverse of that nonlinear function to create I out. So we're using Q1 to pre-distort the I in signal. That means we're deliberately leveraging the nonlinear operation of these devices, and we don't rely on a small signal model here. That's cool, and it's also why I've been using total signal notation throughout, so these are both total signals. Alright, back to relating IC1, which is equal to IC2, to I in. First, we observe that IC1 has to be beta times IB1 because Q1 is in the forward active region. We know it's in forward active because it's diode connected, and diode connected devices are either in forward active or cut off, and if Q1's cut off, then this is pretty boring. Second, we recall from the previous slide that IB1 has to be the same as IB2 because VB is the same on both devices. Note that this equation is assuming Q1 is identical to Q2, which isn't all that safe of an assumption in normal transistor manufacturing processes. So a mismatch in Q1 and Q2, where like IS1 is not equal to IS2, results in current mismatches, and we'll look at that in more detail later. So we write KCL at the VB node here, noting that two base currents and one collector current flow out of it, while I in flows into it. We can substitute values in for IC1 and IB1 in order to express everything in terms of IB2. And finally, we note the relationship between IB2 and IC2, which is just multiplied by beta, and rearrange a bit in order to find this final relationship between I out and I in. There's a slight mismatch between I in and I out, this beta over beta plus 2 factor, that comes from base current stealing a little bit of I in. And we capture that behavior in an important current mirror parameter called the error factor, or epsilon. Epsilon is the ratio of I out over I in, and for simple mirrors it's about 98%. A 2% error is actually pretty high, and there are lots of trickier mirrors that reduce this error. And in fact, we'll look at one of them in detail in a future video, but we're only going to study that one because this error factor is unique to BJTs. Other transistors like MOSFETs mostly don't have base current. So as a result, this type of analysis, which I call an error problem, is almost never done out in practice anymore. So that means I'm not going to hold you responsible for doing error problems, which is kind of a shame because I find this sort of like KCL math sort of satisfying. But by and large, these are to highlight details about how current mirrors or BJTs work, not for you to practice for an exam. Great. So now we know how a current mirror works and that it basically makes I out equal to I in within a small margin of error. Why do we care? The answer is that current mirrors are very handy for biasing circuits, especially circuits with active loads. Here we've used the Q1, Q2 current mirror to set the collector current of Q3, which we could only do with tricky graphical analysis before. We still need to get VBP right for this circuit to work. But we don't also have a sensitive bias voltage on the base of Q2. And further, it turns out that current mirrors can help us bias Q3 as well, and we'll see more on that later. Now, this hasn't solved all our problems. In fact, we've introduced a new one, which is making this I in current source. Which is weird because we usually only control voltage in lab. But it turns out that making a current source out of structures that look kind of like current mirrors is pretty doable. More on that later too. So we've already talked about error as a parameter of current mirrors, but seeing them in this application as active loads is a hint that there are a few other important current mirror parameters. And it's helpful to define the boundaries of our current mirror when we talk about these parameters, so I've included a dotted line that surrounds the current mirror here to show where our current mirror model starts and ends. The current mirror model, by the way, has an input wire on the left and an output wire on the right. In order for the current mirror to operate, we need to make sure we maintain some minimum voltage on the input wire to keep the mirror devices in forward active. And that voltage is called Vin. We also need some minimum voltage on the output wire to keep everything in forward active, and that's called Vmin. And finally, because mirrors are often used as active loads, or even if not, we just want them to behave as close to current sources as we can get, we care about their output resistance. So we calculate the small signal resistance looking into the output wire and call that Rout. And notice that Rout's a small signal parameter, while Vin and Vmin are both large signal parameters. Pause the video and try to find Vin, Vmin, and Rout for this simple current mirror. Vin is VB on 1, because the diode-connected device needs to stay in forward active, which means VB has to be high enough to turn on the Q1 base emitter diode. Vmin is VCE sat 2, because we need to keep Q2 from saturating. And Q2 is guaranteed to be in forward active by VB, which is set by Q1, unless the collector voltage drops too low. So the only thing we need to do to make sure it's in forward active is ensure that the collector is high enough. And finally, an output source connected to the output of the mirror, if we tore off all of the rest of this amplifier up here, would just see RO2 to ground. That's because the GM generator in Q2 would be shut off, since the base node here would be hooked to ground through a single resistor of 1 over GM, which represents the diode connected device. Any rate, so the upshot is that the Rout here is just equal to RO2. In summary, current mirrors set I out to be pretty close to I in. BJT current mirrors have small error factors, which we label epsilon. Current mirrors can help us bias actively loaded amplifiers. And current mirrors are described by design parameters, and those are Vin, Vmin, epsilon, and Rout.